mesh is distributing the current. It can also be sawing slots in your concrete, like this, and then having the anode ribbon in here and cast it with floating mortar. And on these structures, these are the same bridges as before as a preventive system. You don't need so much current for these preventive systems as you do with where you have active corrosion going on. On these bridges, we had all the cabling is led to the inside of the bridge, except for those two piers that did not, which were solid concrete. So we don't have an issue with ice action on the cabling for this case.
I'm sorry to keep
go ahead.
You installed this impressed current CP system at 2007.
Yeah, it's actually 2007. There was an underwater system installed on both of the bridges, also impressed current. One ground anode bed in each end of each of the two bridges. And in 2008, on one of the bridges, 2009 on the other. Yes, in 2007 below water, 2008 and 9 above water.
Several projects we did consider to use the impressed current system for above water structures. The major concern I was still talking about years back is that it's hard to maintain. I don't know if you have heard of this. At least 6-7 years ago, they did a survey. FHWA did a survey, and actually over 50% of the impressed current CP system is not working, or not working properly. So it's just a waste of money to maintain them. Do you have those experiences?
It's not a waste of money to maintain them. It's a waste of money if you don't maintain them.
Yes. That's good.
And that's true, and that's part of the history that lies with impressed current systems. That many owners they install it and then they forget to operate and maintain it. I think with automatic monitoring system that is overcome more or less.
How much power? What's the power required per square foot or per square meter?
Yeah, wow! I have to say it in my units. For a system like this, we would say 5 to 10 milliamps per square meters of steel surface. Of steel surface. The steel surface area to concrete ratio is about 1. It varies, of course. Older structures a little less, and the worst I've seen is 2. That's one of those where you can hardly get the concrete between the reinforcement bars. So it's for 1 square meters it's 10 milliamps in design. In operating conditions it might be half of it. So it's a very, very low current. The operating voltages is way below 10 volts, maybe operating at 5 volts. So it's a low voltage, low current systems. Here's just the anode ribbon before it's cast in the concrete.
How do you know you haven't you're not putting too much juice in it?
Yeah, that's monitoring. I'll get back to a few pictures on monitoring on this, but we put in reference electrodes where we monitor the potential between the reference electrode and the reinforcement. Protective criteria would then tell us if we have adequate protection. And at the same time we have design, so there's also an upper limit to how much current density you're allowed to have on the anode material itself.
And when you do this, does it cause the chloride ions to start migrating back out?
Yes. If you have your anode out here, it would cause your chloride ions to go that way. If you have your anode in there, it would cause your chloride ions to go in there.
If you put one
But we don't care about the chloride because we have current that could prevent corrosion. But in principle, yes.
If you turn your current off someday, then you have to take a few more years for it to go back in.
Yes, it will. That's true. And from experience, we did some tests in the early days where the cementitious overlay on many structures, we measure the chloride profiles there. And you can see the chloride is going out in that overlay. We would be surprised if it didn't.
But if it's in a tidal zone, you have a wet, dry, wet, dry.
Yeah.
And isn't that when the tidal coming up, the concrete get very wet?
Yeah.
The ion is very easy passing through the concrete.
Yeah.
And then the next dry cycle, which could just be 6 hours later.
Mm-hmm.
But isn't that your CP current is going to have a major variation here?
It
Yes
has
or
a,
no?
yes, it's a yes or no. It has a big variation. Of course, if you have a sacrificial anode system below water, it will protect the tidal zone and a little more. Same with impress current below water. We did measure simultaneously the water level and potentials. And it's a challenge to do potentials in such an environment because they are affected also by the water saturation and so on. But before doing these, we had trial installations installed in 2001. So we have had some years to gain experience with this before we decided together with the client that it was time to install the system.
Thank you.
Welcome. Drilled in anodes, where you had the conductor bars between the individual anodes. Same basic principles. These are, you can see, there's still also a mesh here in double layers. So there's a lot of steel structure in here. And sometimes we have rails or other structures deep in the concrete. And in order to protect them, drilled in or discrete anodes can be the only way of doing that. Conducting mortar is also a system. It's nickel-coated graphite fibers, and the principle is, of course, that between these fibers you can have your current conducting. It's been used in quite a number of places. We did some trial installations on this and found that it did not remain adequate conductivity if you are too far away from water. So we did not use that.
What is this zinc spray?
This is not zinc spray. This is a cementitious mortar with nickel-coated graphite fibers. Zinc spray and titanium sprays are also systems. Zinc spray, you would expect that they have a limited service life.
That's right.
Yeah.
But it has been found very effective up in Portland.
Yes, on the Philip Highway they have a number of reports on these systems. That's true. These are examples on impress current anodes below water. This is magnetite anodes. This box here is used to cast concrete so that it remains on the seabed level. And all of the cable were jetted down on the sea bottom. This is for fixing on a bridge column underwater. And this is examples of sacrificial anodes. Monitoring is extremely important. How else are you to know that it works as it should do? So it could be reference electrode mounted onto the steel. This is for monitoring below water level for a zinc reference electrode. Operating and communication systems. Many systems today have power modules for individual anodic cells or anode zones, so that if they fail, you can take it out and replace it with a new one. And this is the computer data logger, where you also have a software program and you can access all the data both directly on site in your bridge or remotely. It is a lifelong operation maintenance, and any owner would need to know that. If they're not willing or capable of doing that, they should not have cathodic protection. So you have functional requirements. You need to have current and voltage applied to the system, and directly to potentials. You need to be very careful about where you have your reference electrodes. If you place your reference electrodes very close to your anode, you'll probably find very good performance, and vice versa. Yeah, you need to, of course, make sure that everything works at an adequate level. Previously it was manually operated, which is difficult. You go on site once a year, you monitor your system, you go back and evaluate your data and find out you have to adjust your current, go out and you have to do it once again. With the automatic systems, you can monitor from your office, and you can adjust from your offices as well, so that's very time saving. And also, as I write down here at the bottom, you also have alarm options if there's a current failure. You can get information either as a text message or on an email, or if you have some measurements that are outside range. We did that on one of the systems where we had the client in on that he got a text that something was wrong, but then he was woken up in the middle of the night with current failure on your bridge. And it's not that important to know that at that time, so he's not receiving those messages anymore. Again, the power modules, you have your reference electrode, anode cabling, cathode cabling. And we use GSM modem is one way of transmitting data. It can also be fiber optic cables for data transmittal. Very often we would ask for a sketch of the structure, where you directly can look at the potential and the protective layer. Or window space, which is the most updated ones. And you also have indicators telling whether things are operating as it should do. It's widely used. This is a project we did in the Middle East. It's a petrochemical industry. You can see labor is very cheap, so they gave them all hammer and chisels to do the breakups of concrete. One challenge with this was the large amount of steel plates being in contact with the concrete. That was actually a very large surface area that needed to be taken into consideration in the design. An example, this is not a COBE project, but a contractor took me out on site. You can see they do old funny islands in the Middle East. You can live on a fish. And this is a case where they, on these artificial islands, they had 13 bridges installed as preventive system, precast elements. The selection was based, and we see that more and more in the Middle East, that because cathodic protection as installation cost is cheaper than maybe stainless steel, some clients ask for that to be done. So these are the, I think we had it earlier, the anode ribbons, titanium, the current conductors. The tunnel in Korea, Busan Gyo Tunnel, the very deep immersed tunnel. There are some areas in the lower ground areas that could contain some sulfate, so there was a concern with the steel M-frame between the tunnel segment that it could cause microbiological corrosion. We advised that they used duplex steel, high-grade steel. As they don't produce that in Korea, they asked for a cathodic protection system. So we designed for a cathodic protection system impressed currents, where there's a sacrificial anode system in temporary phase before you have it installed on site. And then we have impressed currents anodes around the circumference on concrete, just protecting the anode during casting. So they're placed here along the steel end frame. And here you can also see the scaffolding down there. Another project in Sweden protecting the edge beams, 6 kilometer long